Slab induction heating power. A preheated slab is placed in the inductor. The current in the inductor is 12.5 kA and the frequency is 150 Hz. The task is to calculate the joule heat power produced in the slab. I'm going to draw the cross-section of the slab in QuickField, specify the current in the coil, and QuickField will calculate the current density distribution in the slab and the joule heat power. Okay, let's start QuickField now. In QuickField, I create new problem, slab. Next, problem type is AC magnetics, frequency is 150 Hz, model class is two-dimensional plane parallel, and the slab thickness, the axial length, is 1200 millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I'm going to draw it here from Sketch. First, I'm going to insert a rectangle with the dimensions of 600 by 100 millimeters. The insert point will be this one, and it should be located 50 millimeters above the horizontal axis. Insert. This would be the inductor. Now I need to insert a conductor, a circle with a diameter of 30 millimeters. Insert, and another circle with a diameter of 20 millimeters. Insert. Now let's zoom in and put the circle in proper position here. Then I need 10 copies more. Right click, duplicate selection, displacement by 50 millimeters, and I need 10 copies more. Okay, now let's move it to the right by 10 millimeters. This is the upper part of the inductor, and I'm going to duplicate this to get the bottom part. Right click, duplicate selection by the symmetry along the horizontal axis. Okay, this is the bottom part, and I need to insert the slab in the model. So I'm going to insert another rectangle with the dimensions of, in fact the slab is much longer than the inductor. I will insert the rectangle with the width of 2000 millimeters and the height is 120 millimeters. So I will have the slab extending to the left and to the right. Insert. Oh, it looks I put the inductor in the wrong position. Undo. This point should be 50 millimeters above the slab surface, so I need to select this and move it up by 60 millimeters. And this one I will move down by 60 millimeters. Now insert a rectangle with the dimensions 2000 by 120 millimeters. Insert. This is correct. Now let's assign labels. Through labels we can explain the geometric object's meaning and provide the physical properties. Switch to Select Objects mode, click the object to select and type in the label name here. This is slab. This one and this one are insulation. To select multiple objects at the same time, hold the Ctrl button pressed. These are conductors with the current flowing to us, the positive direction of the current. So I assign label I+, and for these conductors I assign label I-, and these are hollow conductors. Inside is water. Again, you need to select multiple objects. I'm going to use the rubber band. This is water. and these are water. In fact, the magnetic field is distributed not only in the slab and in the coil, but also in the air outside. So we need to add the air block here. Switch to insert mode, change the line type to the half arc, and draw the air block boundary. Switch to select mode, click to select and assign the label air. And I should assign the label to the external boundary. Again, hold the Control button pressed to select multiple objects, external. Now let's provide physical properties for these labels. Double-click the label name in the tree. Magnetic permeability of the air is 1. For the insulation, I specify permeability of 1. For the water, I specify permeability of 1. Far away from the inductor, the magnetic field fades to 0. So at the external boundary, I specify 0 magnetic potential value. For the I+ label, it is a copper conductor, so the magnetic permeability is 1, and the current value is the total current, 12,500 amperes. This is the root mean square value of the sinusoidal wave. I need to specify the magnitude here, so I need to multiply this value by the square root of 2. And the conductors are connected in series. Let's copy this. Okay, for the I-, magnetic permeability is 1. Total current, the same magnitude by the negative sign, and conductors are connected in series. And for the slab, above the Curie point, the magnetic permeability of the slab is 1, and electrical conductivity is a function of temperature. I have the dependency here in the text file. Just copy it and paste it here. Okay. And the total current in the slab is 0. Okay. That's all for the geometry model and the material properties. Before I can start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. Let's zoom in. These field lines and the color map look unnatural. There should be no sharp corners on the field lines. Let's use Solve and Refine option to get more accurate results. Solve and Refine, okay. Let's take a look at the results. Again, let's zoom in. Much better. Okay, here you can see the parent density distribution. You can switch the color map to the Joule heat power and see the power density distribution in the slab. You can use the contour tool, draw the line here, and take a look at the power density distribution along this line on the XY plot. You can also draw the contour along the slab and get the power density distribution along the contour. This part is located under the inductor, and these parts are located outside the inductor. You can also use the contour tool to calculate the integral values. I'm going to click inside, so you see the entire slab is selected. Follow to the integrals and calculate the Joule heat power. The total power produced in the slab is 436 kilowatts. And what about the temperature? To calculate the temperature, you should simulate a transient thermal problem. Okay, I create a new problem. slab underscore HT, next. Problem type is transient heat transfer, model class is the same plane parallel, axial length is 1200 millimeters. To be able to pass the power density distribution from magnetic to thermal problem, both problems should be based on the same geometry model file. So here in the geometry model section, I should type in the file name that was used in AC magnetic problem. This is the AC magnetics. The geometry file name was slab.mod. Okay, next. Here I should specify the integration time parameters. I'm going to simulate the 10 seconds period with the intermediate time step of 1 second, and the initial slab temperature is 900 degrees Celsius. Finish. You see the geometry model is the same in AC magnetic and the heat transfer problem, and the labels are the same. Here I should only provide physical properties for the labels. In thermal problem, I specify thermal properties. I'm not interested in the temperature distribution in the air, so I do not specify any properties for the air. Just click OK and you see the exclamation mark next to the label name. This exclamation mark indicates that this label is excluded from the analysis. I'm not interested in the temperature distribution in the coil as well, and in the insulation, and in the water. The block I'm interested in is the slab. So for the slab, I specify thermal conductivity of steel, which is 24. The density is 7,880 kilograms per meter cubed, and the specific heat is 730. I do not specify power loss here, as I'm going to import loss distribution from the magnetic problem. Okay. And for the edge labels, I do not specify any properties as well. Next to the edge label, you see the 0 mark. That means that this label doesn't affect the results. It holds no data. Now let's specify the link. Open Problem Properties, follow to the Links tab, choose the data type Generated Heat, browse for the problem. It is located here. Open, add the link. Okay, now I can solve thermal problem. And here you can see the results. The temperature rise over 10 seconds period was 48 degrees. Let's zoom in and switch off the isotherms. Here you can see the temperature distribution in the slab. Again, I can use the contour tool and take a look at the temperature distribution along the contour on the XY plot. 900 degrees in the center of the slab, 948 at the surface. In fact, the slab is cooled by the air, and the heated body radiates the energy. Let's add the boundary condition to the thermal problem. Open the geometry model, zoom in, and switch to select objects mode, and for the slab surface assign the label surface. For this label I specify the radiation boundary condition. The ambient air temperature is 20 degrees Celsius and the emissivity coefficient is 0.8. Okay, let's solve the problem again, and we've got an error message. The linked problem results are out of date. Linked problem is magnetic problem. Why the results are out of date? Remember, both problems share the same geometry model file, and we have modified the geometry model file. We have assigned label to the surface of the slab. We have provided physical properties for this label in thermal problem, but we also should provide physical properties for this label in magnetic problem. Okay, in fact, this label doesn't have any physical meaning in magnetic problems, so I didn't specify any properties here. Just click OK. Again, you see the 0 mark next to the label name. That means that this label doesn't affect the results. Anyway, the data file has been modified and the geometry model file has been modified, so we have to solve the problem again. Solve magnetic problem. Let's take a look at the results. To validate the results, I'm going to calculate the total power in the slab. Again, use the contour tool, click the slab to select integrals. It was 436 kilowatts. 436, exactly the same value. So now I can solve thermal problem. Remember, the temperature was 984. What would be the temperature now? Let's take a look at the results. I do not like these broken field lines. Let's solve and refine. Okay, I need to solve AC magnetic problem first. You see, QuickField has built much dense mesh in the slab. Let's take a look at the results and now solve thermal problem. Open the results. Now we have a nice field picture with the smooth isotherms. And as you can see, the most heated part is located not at the surface but some distance below the surface. That's because the surface is cooled by the air. Let's use the contour tool, draw the line here and take a look at the temperature distribution along this line on the XY plot. Yes, this is the most heated part and it is located about 5 millimeters below the surface. In transient problems, you can select the time layer to see the change in the XY plot and in the color map. Initially it was 900 degrees, then the temperature changed. And the same on the XY plot. This part were heated and this part outside the inductor were cooled by the air. The temperature is not very high, so I'm going to keep on heating the slab. But you should remember that the electrical resistivity of metals depends on temperature. In AC magnetic problem, we have specified the temperature of 0 degrees. It's the wrong value. It should be 900 degrees. Okay, let's again solve magnetic problem and solve thermal problem. Okay, now as I told you, the electrical conductivity value depends on the temperature, and we have specified that the temperature is 900 degrees. But now the temperature is 953 degrees Celsius, so we should correct this value. To be able to do so, I create another AC magnetic problem. I will create the problem as a copy of existing AC magnetic problem and call it slab_1. Next, AC magnetics, model class plane parallel, frequency 150 Hz. I'm going to pass the temperature distribution from thermal problem to AC magnetic problem. And to be able to pass data from one problem to another, the problems should be based on the same geometry model file. Finish. The geometry model is the same and the material properties are the same, but now instead of specifying the temperature here, I'm going to import the temperature distribution from thermal problem. So open the problem properties, links, temperature field, browse. That's the thermal problem. Open, add. Remember, in the thermal problem there are several time layers. I need the time layer of 10 seconds. Update. Okay. Solve the problem. Let's take a look at the results. Now let me check. When the temperature was 900 degrees, the total power generated in the slab was 1.05 megawatts. Now, with the temperature of 953 degrees, the power generated in the slab is almost the same value, but still there is some difference. And remember, the power distribution is not uniform. Okay, now I have the new power distribution in the slab. Let's keep on heating the slab. I create new problem as a copy of transient heat transfer problem slab underscore ht underscore 1 next. Again, the problems should be based on the same geometry model file. Next. Again, I'm going to simulate the 10 seconds period of time, but now the initial temperature will not be 900 degrees. I'm going to import the initial temperature distribution from the previous heat transfer problem. So follow to the links tab, delete this one. I need the generated heat from the slab underscore 1 problem, and I need the temperature distribution from the heat transfer problem. And I need the temperature distribution at the moment of time 10 seconds. Update. Okay. Let's solve this problem. Let's take a look at the results. This is the temperature distribution after next 10 seconds of heating. Let's adjust the field picture and select the time layer of 0. You see, it is not 900 degrees uniform temperature distribution. It is the temperature distribution that was calculated after first 10 seconds period of heating. Now we have another 10 seconds period of heating. And if you plan to keep on heating the slab, you need to create another magnetic problem to take into account the actual temperature distribution and actual value of the conductivity. And this magnetic problem should import the temperature distribution from the slab underscore ht1 problem. Solve the problem, get the new value of the power, and pass the power distribution in the next heat transfer problem. This way you can continue building the chain of AC and transient heat transfer problems, and QuickField will automatically adjust material properties with the temperature variation. If you search for the slab induction heating power on our website, you will find the example page. Here you can read about the problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. The simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.